Hi everyone, I'm Niall Clancy with the University of Wyoming, and my talk today is on the vulnerability of warm, cool, and cold water fishes to stream warming in Montana and Wyoming. Now most large rivers start as cold headwater streams that become progressively warmer and larger as you move downstream. The preference for certain temperatures along this gradient is how we generally classify fish into the three primary thermal guilds: cold water, cool water, and warm water. Now, many studies have shown that stream warming due to climate change has negative effects on population persistence of cold water species. In the Montana and Wyoming region, climate-driven declines have been shown for bull trout, for cutthroat trout, and for Columbia slimy sculpin, and they've been predicted for burbot. Put another way, populations of these species are most likely to persist in the long term at a certain temperature and decreasingly likely to persist above or below that temperature. Above a certain higher temperature, long-term population persistence becomes unlikely. And as greater proportions of streams warm to above that temperature, more populations will continue to blink out. But how well does this pattern apply to cool and warm water fishes? Are they also vulnerable to stream warming? Well, we know of some well-documented non-native species, such as smallmouth bass, shown here where blue represents the locations of where bass have been found before 2000 and pink after 2000, where these species are moving upstream as previously cold locations become thermally suitable as they become warmer. Now, this pattern has been documented in our region for smallmouth bass in the Laramie River, the Yellowstone River, and the Powder River. There's also been a few studies that predict declines of cool or warm water fishes in this region, specifically for fine-scaled dace in the Black Hills, plains top minnow along the Wyoming-Nebraska border, and Arctic grayling in southwestern Montana, which are technically a cool water fish. But what about all of the other native cool and warm water fishes, most of which are far less frequently studied? Well, so the purpose of our study here is to identify which of all the native game and non-game fishes in Montana and Wyoming are likely to be vulnerable to stream warming, and then to compare across the three thermal guilds. To look at species temperature relationships on such a large scale, we need a large-scale temperature model, the premier example of which is the Forest Service's Norwest Stream Temperature Model. But we're missing a large portion of eastern Montana and a small portion of northeastern Wyoming. So in 2020, these 10 nice people here set out 65 temperature loggers for me across eastern Montana, or provided me with previously collected stream temp data. And thanks to the data that they collected, along with the modeling work of Sherry Woolrab and Gwen Chandler at the Rocky Mountain Research Station in Boise, we were able to fill out Norwest for both states, just with the exception now of this small portion of eastern Wyoming in the Niobrara Basin. This completed Norwest model has mean August stream temperature projections for the 2000s, which is the average of August temperatures from 1993 to 2011, as well as predictions for the 2040s and 2080s. One thing to note is that the 2040s and 2080s predictions are based on the A1B greenhouse gas emissions scenario. And that's a scenario that we are currently exceeding by more than a small margin. Now, to determine what fish prefer what temperatures, we also had to build a large fish occurrence data set. So we compiled data from all of these different groups' databases, as well as reports, to create a final data set that has over 38,000 unique locations by month for 116 species or subspecies of fish. You'll notice that I've included data from Idaho here, and that's because some of the species in western Montana didn't have access to as warm of waters as they could tolerate if I only looked at western Montana. So I include Idaho data to determine species thermal niches, but I don't include that in any of the analyses. So to calculate a species thermal niche, we looked at the full spread of predicted Norwest temperatures at the sites where a species was present. And then we set an upper value meant to indicate where the likelihood of long-term population persistence drops off at one standard deviation above the mean temperature. So that upper niche value is set at a value where 84% of occurrences were at or below that mean August stream temperature. To look at that visually, we have sand shiner locations shown here in red. And the mean temperature of those sites is 20.3 degrees C, with one standard deviation above that, the upper niche value, at 22.1 degrees C. Now, because the determination of whether or not a species is thermally vulnerable really hinges on picking this number, I just want to talk a little bit more about what this number is and is not meant to represent. So if we look at our upper niche value for West Slope cutthroat, we see that it is far lower at 12.8 degrees than published thermal tolerance values such as the upper ultimate incipient lethal temperature of 19.6 degrees. But that's because we're getting at something different. The UU-ILT or other lab-derived physiological values are good at telling us what a species can tolerate on a time span between a few hours to a few weeks. So they're great for things like deciding when there should or shouldn't be fishing closures, or for when there should be hoot owl restrictions. But our upper niche value here is meant to represent the mean August stream temperature at which a population can persist for decades. So that means a temperature at which eggs, fry, and juveniles are likely to survive, and where that species isn't as likely to be outcompeted by other species. So while there are pros and cons to this approach, I think it makes sense, especially since the numbers we come up with are very close to those found or used in other studies of long-term population persistence in the field. Granted, that's only for the handful of species for which those studies have also been conducted. Okay, so with that, we had 55 native species for which we had enough data. And please don't try to read all of these species names. It's just to give you a sense of the thermal guilds, warm shown here in red, cool in pink, and cold in green. A few species that aren't included that people may be interested in, horny head chub, fine scale dace, and pea mouth just didn't have enough data to be included. And then we removed burbot, leather-side chub, pearl dace, and mountain whitefish because our thermal niche approach provided obviously incorrect values. I suspect because these species are finding different thermal microhabitats that a landscape level temperature model just can't account for. So that left us with 5 cold, 14 cool, and 36 warm water species. We then removed all species that were often found at the highest temperatures within their range. So back to sandshiner, if we look at the spread of temperatures at all streams within their range, which we show here in dark gray, we see that they are most often captured at the high end of this range. So they aren't likely to be too stressed by temperatures at the higher end of the spectrum here. So if we apply that to all 55 of those species, that removes most, the ones that we at least can't say are particularly vulnerable to the highest temperatures they might experience. And that leaves these 15 species. We further removed 4 of these because they occur more often at sites above their upper niche value. For Iowa darter, red-bellied dace, and red shiner, I again believe this is due to them finding cooler pockets of water than what Norwest can model at a landscape level. And then for red band trout, it's probably a reflection of hybridization with non-native rainbow trout that makes the data very messy. So that leaves us with the unlucky 11. The species we are fairly confident are thermally sensitive within the region. This includes 4 cold water species: bull trout, cutthroat trout, Columbia slimy sculpin, and cedar sculpin, which is 80% of the cold water species we examined. The cool water species are Arctic grayling, Colorado sculpin, and Rocky Mountain sculpin. And both of those sculpin are species that were recently split off from mottled sculpin. So basically what is referred to as mottled sculpin in the Missouri River Basin for Rocky Mountain sculpin and Green River Basin for the Colorado. and that's 21% of the cool water species we examined. And last, we have plain sucker, that's the mountain sucker species in the Missouri Basin, as well as creek chub, lake chub, and plains top minnow, which represents 11% of warm water species. Now, all 11 of these species are found more often at locations with temperatures under our upper thermal niche value, which I think is evidence that the method that we are using is at least getting at an ecologically relevant temperature cutoff. And perhaps the most important, biggest point of this presentation is that 10 of those 11, all but Arctic grayling, are already found less frequently at locations that are predicted to be cool enough now, but too warm by the 2040s. And to me, that indicates that declines are already underway. Okay, so let's look at each of the different species groups and their predicted declines. We see that salmonids are expected to decline between about 50 and 70% by the 2080s. This is decade on the x-axis and proportion of historically occupied sites that are predicted to be too warm on the y-axis. Compared to recent work by Donovan Bell, Drs. Kovacs, Mulfeld, Alchokachi, and others, these numbers are similar for bull trout and higher for West Slope cutthroat, which are shown as the striped bar within the cutthroats here. If we look at the sculpins, Columbia slimy sculpin we expect to decline by upwards of 55% by the 2080s. And Michael Lemoyne and others found Columbia slimies to already have declined by almost this much in the Bitterroot drainage currently, which means our prediction for them may actually be low. So if you compare to other studies, our predictions are sometimes higher, sometimes lower, and sometimes very similar. So to me, I think it's important not to view these predictions as hard numbers, but more as ballpark estimates that are only accounting for temperature. There's other factors that I didn't look at here. We also see that Colorado sculpin have some pretty major potential declines, though I think over 20% site loss for Cedar sculpin and Rocky Mountain sculpin is also not insignificant. Our lone sucker, the plains sucker of eastern Montana and northern Wyoming, we predict to decline somewhere in the region of about 36%. And then the minnows and top minnows, we predict creek chub and lake chub to decline somewhere in the 45% range, and plains top minnow by about 34%. Again, not hard numbers, but rough estimates. So some general conclusions. It does appear that cold water species are the most vulnerable to stream warming overall. However, there are similar numbers of species of all thermal gills that are vulnerable. This means that all regions in both states have species that are probably declining from stream temperatures warming. 2, this is far from just a salmonid problem. Quite a few non-game species, both cold and warm water, need to be accounted for when we're doing climate adaptation or conservation projects. And compared to salmonids, the other vulnerable species are small. They're small-bodied fish, and they probably can't move as easily or get over barriers as easily to access new thermally suitable sites, meaning their ability to shift their range is probably far less. And then lastly, I'll just note that our approach here may not be as useful for large river fishes. Plenty of them still could be thermally vulnerable, but I just think we can't get at it as well at this landscape level approach. And I certainly don't think that this should be taken as the final word on any of these species, though I think it is certainly getting at something of the truth. And also, I think we are more than likely guilty of omitting species in the final list than we are of including too many. Moving on, I plan to translate this work into online maps of thermal refugia that people can interact with, similar to the Forest Service's Climate Shield for bull trout and cutthroat trout. And we'll also be working with a new master's student to incorporate drought and stream drying. And then last, I hope to look into the remaining species that were either misclassified or data deficient. So with that, here's a huge list of people who made this project possible, and thanks of course to the NSF and Forest Service for funding the research.